So let's keep going. All right. So I'm hoping to give you, and maybe I'll go a little bit quicker here, like an overview of all of the data structure, and then to, on the board, go through one of the pieces of it, okay? But here is the data structure. So, right, so it's this, we need to solve the L1 min ratio problem. We need to do it while updating gradients and lengths. We only need to do it approximately. We need to route flow along cycles when we find them. And just to mention only once, there's something tricky, but fortunately standard, like this happens even in very old algorithms, about the third point, which is that these cycles, they don't have to be short in like a combinatorial sense, okay? So it's really possible that throughout the algorithm, we're routing m circulation or cycle flows that each have length order m. Okay? So the total representation size seems to be m squared. But it turns out that as long as you're only sending flow along trees, you can have a data structure that will do it for you. Okay? So because we're sending the flow along a tree, there is a data structure that will sort of keep track of how much flow you're putting on the tree edges in a cheap way. So you don't really pay for this. Okay. So the data structure maintains this small set of trees for us where we can find cycles. And then the whole algorithm is just, we're running our IPM, we identify a good circulation that approximately updates things, then we update our flow. Then the interior point method tells us like, what are some gradient entries and some length entries that need to update. And I wrote lazy because if they've changed by less than as a factor 1.1, then you don't update them. Then you need to update your trees, and then you keep going. Okay, so that's the overall picture. And you just keep going. At the end, you have your final flow, and now you round it to be an integer flow. And that's super simple. It's just you look at like every fractional cycle, like edge with a fractional flow on it, and one direction of rounding it will bring you like to at least as good an objective, and then you get the optimal flow. It's a detail. Okay, so let's talk a bit about this dynamic min ratio cycle problem, just super, super high level, because we want to zoom in on some parts. So we're going to, instead of sampling a low stretch tree, which was our warm-up, we're going to only partially build the tree. Okay? So we'll build a tree that covers, say, 99% of the vertices. That means that we haven't really connected everything. It's a forest instead. Okay? So we just build a forest. And the forest kind of, if we contract it, there's still 1% of the vertices left. So maybe let me draw a picture. We have not a tree. We've instead built a forest, okay, a spanning forest. And then we'll contract each component of that forest into a vertex, and we still have 1% of the vertices left. Okay? And now we can recursively build a tree on the rest. Okay? Now, this then allows us to appeal to the magic of recursion. Okay? To maintain the trees, what we'll do is we'll say, okay, we had a forest at this level. Now the IPM comes over and says, this edge just got really long. Okay, so it's not really a good edge to route along anymore. Then we'll cut this forest connected component into two pieces by deleting that edge. And so now we have another vertex appearing in the recursive thing. So we find a forest, contract. If the forest gets damaged, you just take out the edge, give up, and say, magic of recursion, save me, right? See, and then by magic of recursion, like now this building a tree for the next level has to also handle that extra vertex that appeared down there with some extra edges. Now, there are some challenges in carrying this out. Okay? The recursion of contracting vertices will reduce the number of vertices in the graph. But it's actually not really going to reduce the number of edges. You're just going to move the edges onto like each connected component contracts into one part. So this, like forests, will allow us to reduce the number of vertices, but we also need to reduce the number of edges, okay, to kind of recursively build the tree. But that's where expanders will help us, because expanders in my world are really about like reducing edges or dealing with edges. Okay? And then we also need to deal with the fact that like we're then solving some recursive problem that we need to like maintain over time as the problem is changing, right? So we get like changes to the top level, then we pass these changes into the recursion, and now we need to deal with them. That means that our smaller graphs are changing in weird ways. So for example, here I had my forest connected components that I contracted each component into a vertex. That gave me my recursive problem. Then suddenly one of the vertices from the like perspective of this level of the recursion broke into two. Okay, and so now I need to like deal with weird updates like my vertices are splitting. Okay, so overall though, we're going to then start with our initial graph. Then we're going to do this vertex contraction business to get a graph with fewer vertices. Then we're going to do something else to throw edges away, and now we have a graph with both fewer vertices and fewer edges. Okay, so that gives us our next smaller graph. So let's forget about the vertex count. Let's just think about the edge count. It's been divided by some k, which is a large number. Okay, and now we're just going to keep doing that to some depth d, where g is essentially a single vertex, the level d graph. Okay, and now we have m over k to the d edges left, so I'm saying this has to be 1, right? So we're just going to reduce the graph size all the way down to 1. And that, at that point, we'll have built our tree, for example. So that means, right, just to say it out loud, that m should be k to the d, or that k should be m to the 1 over d. Okay? And the depth that we're going to use is going to be something like a depth, a recursion depth of, say, log to the 0.1 of n. Okay. And we'll get to a little bit more about these parameters. We're not going to understand all the parameters. We're just going to understand the general philosophy of the parameters at some point. So in this original problem, the opt min ratio cycle has a value of -1, approximately. Now we're going to mess up the graph, right? We're going to approximate it with a smaller graph, so there won't be as good an update left anymore in the recursive problem. So now I'm not thinking about building a tree anymore. I'm just thinking about like from how much did I mess up the min ratio instance by mapping it into a smaller graph. Okay. And I lost some factor beta. And basically, I'm going to lose a factor beta at every level in a multiplicative sense. Okay? So at the bottom, I've messed up my min ratio cycle by a factor beta to the d. Okay? Now, the question is, with the depth being log to the 0.1 m, what kinds of beta can I afford and still have the approximation factor be m to the little 1. Right? But the answer is I can afford quite a lot. Suppose that I take beta to be 2 to the square root log m. Okay, that's a subpolynomial, but much larger than any polylog factor. And now I raise that, so beta to the 0 to the d is beta to the 0.1 m. That's then log to the 0.5, the square root, to the 0.1, of m. And then I just end up with 2 to the log to the 0.6 m. Okay. So generally speaking, there's going to be a lot of subpolynomial factors floating around. And the main thing that we need to make sure about is that when you raise them to the power d, they're still small. Okay? And this is like something that you can horrifically abuse. Like you can really do a lot of crazy things with terrible approximation factors, then raise them to a power d, and they're still subpolynomial. There's one exception to this. There's one number in the whole algorithm that you cannot raise to a power d. And that's k, the size reduction factor. If you somehow lose a factor k of something everywhere in each level, then you're dead, because k to the d is m. So there's a lot of different somewhat small numbers floating around, but really one of them is the big one, that's k, and everything else is small. Now, here's another thing that we need to cope with, which is that we'll get an update from the IPM to our top-level graph, right? Then sometimes that will split our forests and stuff, right? So the next graph changes in a weird way. Now, we'll make sure that we can bound the number of changes in terms of the number of edges that look different now in the next level by some factor r. Okay? But now that's going to happen across every level. So we're incurring r updates at level 1, and then r squared at level 2, r to the d at the bottom. So this number of updates, like how much they multiply, is another one of these numbers that has to be small still when you raise it to a power d. Okay? So it's just like there's some kind of hierarchy. One number is the big one that you cannot afford to raise to a power d. All the other numbers have to be smaller in some sense, smaller subpolynomial factors. This number of updates that we get extra at each level in a multiplicative sense, this is called recourse. That's another thing that has to be a smaller number. Okay, so now let's talk a little bit about the steps of reducing the size. So we said that the first part is that you have your initial graph with m edges, and let's say it also has m vertices, just because I don't want 2 parameters. I just want 1. Okay? And now we're going to find a forest here in this graph, and then we'll contract the components of that forest. I think of them as having roots, so it's just that everything else contracts into the root. And now I have a smaller graph with m over k vertices. Okay, so there's some size reduction factor here, basically saying that the number of connected components was m over k. Then I did not do anything to remove edges. Okay, so in principle, it's possible that every single component that I was contracting, all the edges were leaving except for the forest edges. So maybe no edges disappeared at all. So the graph still has m edges. So we call this step vertex sparsification. And then we need to do edge sparsification. So now we're going to take that same graph now with few vertices, and then we're going to throw away most of the edges. So we call the middle graph the core graph, and then we do edge sparsification, then we call it the sparsified core graph. And this is the part that I'm hoping to talk a bit about. When is it we finish? Okay, yeah. So this is I'm hoping to talk a bit about the edge sparsification parts a bit more. Not so much about the vertex sparsification part. So in flow algorithms, okay? An hour, okay, good, yeah, thank you. So just to say something that, like I picked the edge sparsification for a number of reasons, okay? The first reason is arguably laziness, okay? It's going to be a lot easier for me to explain. So somehow there's something about vertex sparsification that we don't understand nearly as well yet. I think we don't have all the right tools yet, okay? Now this connects to another thing, which is that in my world, expanders that Thatcherpole told us so much about the other day, expanders are in some sense telling you how do you approximate a graph with a complete graph, because expanders are like a complete graph, but also as a bonus, it's sparse, right? So it's like you get to say my graph just consists of a collection of blobs. Each blob is basically a complete graph, except also I have a sparse representation of it. But that's not the whole story. Okay, there are lots of problems that are still hard on a basically complete graph. Okay. Now, the other side of the story is sort of saying, how do you approximate, so vertex sparsification, the way we think about it at the moment, how do you approximate a graph with a tree? It's like the opposite thing. Are you going to approximate your graph as a complete graph or as a tree? And these do very different things for you. So approximating it as a tree will help you reduce the vertex count. Approximating it as a complete graph will help you reduce the edge count, and these are not the same. Okay? And we do not know at the moment how to get any interesting vertex sparsification via expanders. Okay, it's a different set of techniques. That would be very nice to have. It doesn't work. There are some papers that do it, but they only do it in unweighted graphs, and it's fundamentally not acceptable as like a tool. It doesn't help inside other algorithms. Okay, let's talk briefly about this picture of contracting forest components, right? So here I have my graph. I have a forest shown with blue edges, and I have root vertices. Okay? And now in the contracted thing, each of those like connected components gets contracted into a vertex. Yeah?
Sorry, can I just ask a question about the general setup? So like when you were first describing this and talking about those sort of spanning trees that are like, those sort of spanning trees and all the vertices, what's the utility here of like using like those sort of spanning trees that only cover most of the vertices and help you deal with like the dynamic stuff? Or?
So the question was like, what is the point of only covering some of the vertices with these forests? And yes, the answer is that now, like when an edge, it's going to help us dynamize things. When an edge gets destroyed, we'll then only handle it at this level of building the forest by just giving up on it. And then the next level, we'll have to work out what to do with it. And that doesn't sound like much of an answer, but the trick is that like at the next level, it'll be cheaper to rebuild the graph. So because the next level is a smaller graph. So you're sort of always passing the challenging update problem into a small graph that you can then cheaply repair. Does that help a bit?
Yeah, like morally, I guess it makes sense.
Okay, morally, the answer was accepted. I think that's the level of detail we can get to on this side. Yeah?
Where are you using the complete graph to reduce the number of edges? What does it mean by using complete graph to reduce the number of edges?
So the question was, how is it that we're using a complete graph to reduce the number of edges? And we'll talk a lot about that. So I won't say too much right now. But basically, the idea is that any uniform subsample of the graph with a rate that brings you down to roughly degree log n will be another expander. And it's basically a complete graph still in terms of all of its connectivity properties, but it's sparse. Okay, so now we got from the IPM that some forest edge changed. So it's not really a good forest anymore. Like this forest had better have short paths. This was sort of why we could contract it, that these edges were short. Now it's not short anymore. Right, so it's not a low stretch tree anymore because we messed up one of the edges, made it long. So then we just give up. We say, let's not use that anymore at this level of building a forest. And then we get 2 connected components instead of 1. And now, down in the contracted graph, that vertex splits into 2. Okay? And then we have like sort of the problem of building a forest on that smaller graph. Okay, so that's all I'll say about the forest part. Okay, there's a lot there, but now let's switch to talking about edges. Also because then we get to sort of build on some of the tools that Thatcherpole told us about yesterday, and I think that'll be nice. So now we're down in this smaller graph, which is dense, okay? So we've contracted components to create a dense graph because we didn't get rid of edges. So this graph is dense. It's not that dense, but I had to have a nice picture. So that's the core graph. Now we want to throw edges away. So we're going to find a spanner. So a spanner is a subgraph, and everything you should think of as unweighted now. It turns out you can. So here we have a spanner, which is just a subgraph with a promise that every edge that we didn't pick has a short path in the subgraph. Okay? So in particular, we'll be able to say that there is a path, which I'm calling an edge embedding, for every edge that we threw away, of length at most m to the little o1. Okay? Now, I claim that, in fact, this means that all distances are preserved in the graph. Can somebody tell me why?
Because each edge is preserved.
Because what?
Because each edge is preserved and every distance is like factor scaled over.
Every edge is preserved, so if I just look at the original shortest path, then I can take like a little detour for each edge in that path. So all distances are preserved. Now, so in spanners, you don't normally actually write down what those paths are. You used to just kind of construct them and say like you can prove that there are short paths. We're going to do more. We're going to actually compute a short path for every edge that we don't put into the spanner. Okay? So these are the edge embeddings. It doesn't have to literally be the shortest path in the spanner. It just has to be short. Okay, now let's make it dynamic. So the hardest thing that we have to deal with is that the vertices could split. Okay? So people have worked on dynamic spanners before, but never on dynamic spanners with vertex splits. And the techniques until this paper couldn't really deal with it. So now if I split that vertex, I break all of these embedding paths, right? So I don't have a spanner anymore. Okay? So how are we going to fix that? So I'm going to describe a procedure that allows me to recover from a whole collection of vertex splits and edge deletions. Okay, so this doesn't have to just be a single vertex split. It's going to be like a batch of updates that you recover from. But to start, we'll understand it by just looking at a single vertex split. Okay. But now we'll create a smaller graph by just marking all the vertices that have experienced a vertex split or an edge deletion insertion, like where something has changed, you mark all of those vertices orange. Okay. Now we're going to try to recover from this vertex split. And what we'll do is we'll try to just move. Ooh, this is going to be unpleasant. And I didn't even get a. So we're going to look at all of the paths that have been broken, and then we're going to move each vertex, each edge, sorry, that has had its path, its embedding path broken. We're going to move it along the embedding path until it hits a marked vertex. Okay? So, for example, let's build a little spanner down here where I can reach it. So suppose this is my original graph. Okay? And now let's say that the spanner excludes these two edges. Okay? So I need to have embeddings for these edges. So I embed this edge with this path, and similarly this edge with this path, right? And this down here is my spanner edges. Okay? So now let's say that this edge gets destroyed. Okay? So I mark the two endpoints of that orange. So this is marked orange, and this is marked orange. Now I'm going to build a new graph on the orange vertices. So here is my first orange vertex, my second orange vertex. And the way I do it is that I take this edge, and then I move it along its embedding path until the endpoint. So the endpoint, I move along the embedding path until it reaches this vertex. Okay? And over here, I move this edge along the embedding path until it reaches another marked vertex. So it ends up looking like this. Okay, it moves there. And similarly, the other one also moves onto these two. Okay? Let's do one more example up here. It's going to look a bit trivial again. So I have these three edges whose paths have been broken, right? So I just move one endpoint along that path until I reach the first place where it's broken in both sides of an edge. That moves one of the edges onto those two orange vertices. I do it for the second one and the third one. And now I have a little graph on the orange vertices. Okay? Now I'm going to build a spanner using these edges on the orange vertices. So let's say that this little graph is J. Can somebody tell me a spanner in this little graph? Yeah? One edge. So a spanner in this little graph is just that I need to pick one of the edges, not pick the other one, and then embed it along that other edge. Okay? So in this particular example, it was super simple. Up here, it's the same thing. I just need to pick one of those three edges. Here I put it into a spanner. Okay? Now I need to compute embedding paths for those. Those are the little dotted lines. And now I have like my spanner and the embedding paths on the tiny graph. It could be a little bit bigger if there were more changes, but I can still make a little spanner and little embedding paths there. Question? Yeah?
So can you see again how we get the three edges on the left side?
The three, so do you see the red embedding paths? Those are the paths that were broken by the vertex split. Now I want to move the edges that have a broken embedding path onto the orange vertices. I move one endpoint along its embedding path until the first time it hits an orange vertex. That puts its end at the top orange vertex, for example. Then I move the other end of the edge along its embedding path until it hits an orange vertex again. And now the edge sits on that orange pair of vertices. So I'm moving the endpoints along the embedding paths until I hit the orange vertices. Is that making sense?
Yeah, but that edge doesn't exist in the new graph, right? Because
So all of my black edges do exist, the orange, and they still exist after the vertex split. But they don't have embedding paths anymore, and now I'm just trying to construct a smaller graph arbitrarily. It doesn't matter exactly what it's coming from, but I'm constructing this smaller graph that's going to help me repair the spanner on the bigger graph. Okay? Now, the question is, I have this spanner. Yeah, question?
So, the whole point of spanner is to not take care of all the edges in the graph. So, but once we have vertex splits, how do we know what edges or what embedding paths are there so that we can move them and construct this vertex split graph, like or the orange graph?
So the question was like, how do we find out which vertices are going, sorry, which edges have had their embedding paths damaged? It's going to be, in some sense, very simple. We're going to write down explicitly all of the embedding paths. So just at every vertex, we know every single other edge that's embedded through it. So we can just, it's just a list of paths. Yeah. Yeah?
It's like you can view these broken, like whatever you're doing, as like a mapping between old broken embedded paths to edges of these orange ones.
Yes. So the question was, I can picture this as I'm trying to map the broken paths to edges on the orange vertices, and the answer is yes, that's right. We call it in the paper that we're projecting the edges that have had their paths broken to the little graph. Okay. Now we have a spanner of the little graph. How is that going to help? So we can put that edge in, this blue edge, we'll commit to using it in the big graph. Okay, question?
Yeah, sorry. In the little graph, are you computing is it a weighted spanner where the length of the edges are there stretched in the original spanner, or is it literally unit?
The question was, are there weights anywhere? And the answer is no. There are no weights. Everything is unit weight. The way that we're going to deal with weights basically is going to be that we're going to bucket all the edges by weight. So we only ever create a spanner for a set of edges that have the same weight or the same length. And then we never need to add weights. There's something non-trivial about making that always work, that we never add weights to anything anywhere, but we're going to commit to that. That's going to help us a lot. Okay, so now we're going to bring in that blue edge, which was the one like we picked in the little spanner. We're going to put it in the thing it corresponded to back in the big graph. Now the question is, what are the new embedding paths? Okay. So now let's construct an embedding path for one of the other edges. The way you do it is you move it to the orange vertex. Then you walk down to the edge that along also an old broken embedding path down to the edge that you picked. Then cross that edge that you picked. Then you use a broken embedding path to the orange vertex, and then you go back home. Let's do it like more explicitly here. So which of these two edges am I putting back in? Can someone tell me? The top one, yeah. So because here in J, the prime, the spanner, I picked this edge, I'm putting this one back in. Okay. Now, what am I picturing as the embedding paths for the other edge? I'm picturing, so I need now a new embedding path for this edge that I didn't put in. I say, let's walk to this vertex where it got projected to in the little graph. And because we walked to the first point where the path broke, like that part of the path still exists. Then let's walk along the old embedding path for the other edge back to where the other edge set. Okay. And then let's cross the other edge, walk along its broken embedding path to the orange vertex, then walk along our old broken embedding path back to this endpoint, and that's the other end. So we're just in like the dumbest way possible gluing together embedding paths. Okay? And now we might have to do this more than once. There might be like a path of length m to the little o1 in the spanner, and like each time we're like crossing one spanner edge, then using like a broken embedding path, another broken embedding path to the orange vertex, then crossing a spanner edge, and it's like a horrible amount of zigzagging. Okay? Now suppose that our original spanner, so before we broke things, had a path length of gamma. Okay? Then I claim that the new one has a path length of something like 2 gamma squared. If we also build like a gamma quality spanner on the little graph. And that's going to be an exercise. Okay? So convince yourself of that offline, but it's really like nothing clever. It's being as stupid as possible. And now, of course, my spanner has like a quality of something like 2 gamma squared. That's not so good. Okay? But we repaired all the paths. And also notice that, so I didn't say this very clearly, but how sparse are spanners? So generally speaking, if I get a graph with m vertices and m edges and n vertices, okay, then I can construct a spanner on these n vertices with n to the 1 plus little o1 edges, okay, and a path length, let's say gamma, of m to the little o1 as well. Okay, so up to like some little o1, the degree is going down to constant, right? Yeah?
Statically, you can easily do this with polylogs, right?
Statically, you can easily do this with
but
polylogs.
for dynamic, you really need the little o's one.
Except that even statically, we don't know how to get the explicit embedding paths with polylog length. That was Thatcher Pohl's expander routing question. Yeah, good question. Okay, so you can go down to like polylog or m to the little o1 degree. This means that if I'm making k vertex splits, right, then I'm making repairs on a graph with, say, 2k vertices. If I'm making repairs on the orange graph and it has 2k vertices, right, so I made, say, k vertex splits, then I get that my little graph, so repair graph, has 2k vertices, okay? But then I get that my repair edges are only 2k to the 1 plus little o1, okay? So this is already pretty good in terms of promising me that the repairs to my spanner only use few edges. Okay? It is at the cost of getting like really garbage path length. Like you're making them worse by a large factor each time you do this. Okay? So I think we're going to revisit this in a moment, okay? We're going to do some more details about this because we just saw how to do one set of repairs, and it really messed up the stretch. So we're going to need to fix that. But first, let's finish the slides, okay? So the slides are just going to ask us to think about one more thing. So now suppose that you have this dynamic spanner and everything is great, okay? There's still a big problem. This edge sparsification can really just kill a hidden good solution, right? So suppose here that I have like this hidden good update direction, the min ratio cycle that I'm trying to find, shown in purple. And now I'm going to pick a spanner in this core graph, which consists of the blue edges. So the min ratio cycle is just dead. And it's very possible, from the way we're doing it, that like the gradient could be 0 on every single blue edge, and so there's just no progress left after we deleted the other edges. Okay? So this is horrible. But the embeddings are going to save us. So for every edge that we throw away, we have an embedding path in the spanner. Now, think about embedding the good solution along those paths, right? So whenever you took an edge and you deleted it, reroute the flow of the good hidden solution along those embedding paths. I mean, this is not changing the fact that that solution might now suck, because the gradients could be completely different. But now we're going to consider another set of potential cycle candidates that might also be good cycles. And those are just the cycle closed by every edge that's getting thrown away and its spanner embedding. So I wrote all of those little spanner cycles in green there. And now here's a lemma, which will appear on the problem set, the homework, which you of course don't have to do, but you could if you like having fun. It says that either one of the spanner cycles is a good min ratio cycle, or the embedded solution is still good. Okay? So either I, by the process of sparsifying, discover a good cycle, or I still have a good cycle that I can keep looking for in the recursive thing. Okay? And let's just talk about it for a second, right? So there's some gradient on, say, edge E1. And the only thing that can really go wrong if I don't have like a good gradient anymore, when I've thrown E1 away, is that the gradient along its embedding path is much less, right? So I was getting like, say, a -1 value along E1, and along the embedding path, maybe I get 0. But if that's true, then I have a gradient of -1 and 0 along just E1 plus its embedding path, and that's still a good gradient. Now I'm dividing it by the length of the edge plus the length of the spanner cycle, and it turns out that if you just look at like all of those being good or bad, then like if they're all bad, then you can then argue that delta star is still good. Okay, so it's an easy algebra. And it appears on the exercises. So, but this creates this challenge that we really do have to maintain these embeddings explicitly, right? We needed it also for maintaining the spanner, like dynamically, but also we need it for this. Now, we don't need to pass any information into the recursive graph about them. Okay, so like we need the embeddings to make the graph smaller and to check if they're good cycles, and we forget about them recursively. But we need them at this step. Okay. So like this, okay, we were being very sort of, we switched perspectives a bit between like looking to build a good tree and then saying something very informal instead about how's the quality of the solution changing as we pass things into the graph. Modulo the fact that those two things don't line up, we've now seen the whole data structure. Okay? So it turns out that like these perspectives are a bit equivalent, sort of whether you still have a good solution in the small instance and whether you've built a good tree. Good low stretch tree. So now let's just do a little warning. Our data structure does not work for all query update sequences. Okay, that was the obliviousness or not that we talked about. It's not oblivious at all because we have this graph with like where the min ratio instance lives with gradients and lengths. Then there's this min ratio data structure that finds an update cycle and then feeds it back into the graph. and to deal with it, we used like a white box analysis based on this like f star minus f, this hidden good solution that we knew a lot about how it was changing. Right? Now, this complexity, like how does this help us describe the adversary as something weaker than being fully adaptive? This does not have anything to do with the spanner. So now I get to tell you a bunch of stuff about the spanner without worrying about that. The spanner works against an adaptive adversary. It's only the vertex contraction business that does not work against an adaptive adversary. Yeah. Okay, so a little summary of everything that we saw, and then we can do a bit more spanner. So a single tree can find the first good cycle, but then we're going to recursively partially build trees using these forest components. That's going to help us do maintenance, because when an edge changes, we just ask the next level in the recursion to deal with it. Then we had these core graphs that reduce the vertex count, and we had the spanners that reduce the edge count, and so everything is just getting smaller and smaller. Okay, that was, and then there's something about a new semi-adaptive adversary model. Okay, and yeah. Let's wait with the open problems until the end. Okay, so let's talk a bit more about the spanner and this problem that we were doing something dumb, right? We were patching it in a way that completely messed up what's called the stretch, like the path length in the spanner. It went from gamma to 2 gamma squared. More generally, if you started with a spanner with quality beta, okay, and then so you have a spanner with quality beta, and then you repair it in this way with like a routine that has quality gamma, then you get a spanner with quality beta gamma times 2. Okay. Now, suppose you use such a repair. And now you get another vertex split. Then you do a repair again. What is the quality that you have? It's going to be, you went from beta to this is your new beta, okay? And now you lose this factor 2 gamma again. So after doing, like every time you do a repair, you lose a factor 2 gamma. So with a certain number of repairs, and the quality starting off at, say, 2 gamma, if you have R repairs, you have a spanner of quality 2 gamma power R plus 1. Okay? But the spanner at least had the property of not using too many edges to repair itself, and this is also some kind of stretch. It's something. Now we're going to fix it using, like, I think, reasonably standard batching trick. Okay? Can you see here? Is it too dark if I write on the middle one? Better on the side? Better on the side. Okay, so maybe you're like, I don't care about spanners. So now is a good time to wake up, even if you don't care about spanners, because this batching trick is very, very general. Okay? So how many updates should we survive in our spanner? It's going to be the case that, let's say, we initially start off with the graph having maximum degree delta and also roughly average degree delta. So it basically has n delta edges before we sparsify. Okay, and then it has n to the 1 plus little o1 edges afterwards. Okay. Now, my goal is just going to be to survive through n updates. Okay. Survive n updates. I know that n updates at least with the current scheme, will only cause n insertions or order n insertions into the graph in terms of new edges. So it's still very sparse if I survive through patching n updates. And now I'll just rebuild the spanner from scratch after I survived n updates, and it'll cost me something like this kind of time. And that'll cost me like an overall like amortized time per update if these individual updates take very little time and then I rebuild of like delta, roughly amortized time. Okay, delta being the max degree. So I just need n updates. So let's lay out our n updates. Okay, on like in time. And now let's do a batching scheme that'll give us a running time of n power 1.5. Okay? And then it'll be easy for you to do the full batching scheme. Okay, so it's just like once you have the m power 1.5, going to m to the 1 plus little o 1 is trivial. Okay? I'll still talk about how, but it's easy. So here we start with a spanner of the original graph. Let's call it h. Okay, and it has stretch gamma. Now, let's split this into square root n buckets. Okay. And now what we're going to do to have a good spanner always is that when we're inside a bucket, which now, how many updates are in a bucket if there are square root n buckets? What?
Root n?
Log n? Root n, yes. Root n, right? So there were n updates total. We split it into square root n buckets. So inside a bucket, there are square root n updates. Okay? So my problem is that I cannot sequentially apply the spanner repair many times, right? That kills me, because if I apply it r times and r is big, then I just have like, it grows exponentially the loss in r, okay? So inside this bucket, every time I get an update, I'm going to look at all of the updates here. Sorry, all the updates so far. So let's say we're here. So it's at most square root n, but it could easily be square root n over 2 updates. And then I'm going to build a patch, like this project to the little graph, that deals with all of these. Even though I dealt with them before, I'm going to have to deal with all of them. So now, every time I get an update, I look at all of the updates in my bucket, and I compute a patch. Okay? This might cost me square root n time per update, generally speaking. Okay? But now inside the bucket, I'm always patching this h0. So I'm always doing like h0 plus a patch. So what's the most number of sequential patches I'm applying? What? Not root n. Inside this, it's only one patch, because I'm starting over from the original spanner every time. So I'm always looking at all the updates inside the bucket and then applying a patch that fixes all of them. So it's expensive. But now I only have a single patching. Okay? Then, when I get to here, okay, I'm going to have a patch for all of this. You can also, if you want to, you can actually, yeah, let's say a patch for all of this. It's a better way to explain it. Okay. Now let's call this one h1. Okay. Then inside this bucket, I'm only going to patch h1, but I'm going to do it with all the updates from the bucket so far. Okay? So when I get this update, I'm going to do h1 plus a patch of size at most square root n. Okay? So we're patching h1. Now we have h0, patch h1. So we have 2 patches. Okay? But we never go above 2. So now when we get to here, so we need to get to the second end of the second bucket for things to get really interesting. We're going to look at everything that happened so far, and we're going to do a patch for everything that ever happened. Okay? So this will now be h2, and then inside this bucket, we're going to patch h2. Okay? And so generally speaking, the overall idea is that every time we're at a bucket flag, the end of a bucket, we compute a patch for everything, which you can also think of as just restart over. Then, like with the graph until, but it doesn't matter. We compute a patch for everything. Then inside the bucket, we always patch using all the updates of the bucket to that one that we made at the start of the bucket. And now we never go more than 3 levels, like we never have more than 2 patches applied sequentially. Okay? And what is the overall running time here? Or the cost in terms of number of updates or something? Okay? So inside each bucket, I'm computing a patch with respect to square root n updates. Okay? And how many times am I doing that? I'm doing that so square root n updates, patch of size square root n, and then the total number of times, so let's get this right, sorry. Like the total number of updates where I'm computing a square root n patch is just every single update, right? So I'm doing a square root n patch n times. Okay? So I'm doing a square root n patch n times across the whole thing. How many times am I computing like a full patch, a patch with respect to everything? Square root n times ish. So I have like updates. So in the first category, I have square root n updates. That kind of patch I'm doing n times. These ones I have, say, n updates roughly, but I'm only doing it square root n times. Okay? So altogether, the total number of like volume of patch updates that I'm dealing with is n power 1.5, I guess, times 2. Okay?
Can you repeat what you're doing inside one particular bucket?
Yeah, thank you, good. Okay, so inside a bucket, I guess it's getting a little bit messy here. Inside a bucket, so I have my square root n buckets. Inside a bucket, I'm always taking all of the updates that belong to that bucket that have arrived so far. So like, for example, say I'm getting in the second bucket, I'm getting the kth update of the bucket. That I'm taking all updates 1 through k of that bucket. And then I'm starting from a patch spanner that I computed at the start of the bucket. And then I'm applying a patch with respect to these updates 1 through k of the bucket. So I'm always applying a patch to the start of the bucket. And then I'm like after one more update, I'm just completely applying a new patch. Okay? Now, generally speaking, yeah?
Is this what your algorithm is doing, or you're giving a single case and then you're going to do this 3 cases? Because your game is still spending too much time implementing this.
Yeah, I'm going to address that exactly right now. So this bucketing scheme, okay, it gave us a stretch of 2 gamma to the, let's say, L plus, 2 gamma to the 3 or something. I think we applied like 2 levels of patches and we started with 1 factor gamma. Okay, so this was the path length, 2 gamma to the 3. Okay? Then the amount of work was n to the 1.5. Okay? Or the amount of changes that we made. Let's say edge changes. Total. Because that was the total amount of how many times we took in a patch of a certain size and then patched. This added up to n power 1.5. Okay? But, and this is an exercise, I guess, unless you want me to do it now, but you can do a multi-level version of this scheme, and then you'll get, say you do it with L layers, so you allow yourself to sequentially patch L times. Right now we only did it 2 times. So if you allow yourself to sequentially patch L times, you'll get 2 gamma to the L plus 1 path length, and the total number of edge changes will be n to the 1 plus 1 over L. Okay? Yeah?
These restarters. You have 2 things every root and you restart entirely and you create a new.
So, so it's a good question. So now, we're trying to finish we're trying to have buckets inside our buckets. And I think what we'll end up with is that we started with n updates and b buckets, and then we got n over b items in each bucket. And we had the number of buckets was square root n. Now, we split, one way to think about what happened in this 2-level scheme is that now we split these n over b items into b buckets again, but each bucket only contains one thing. Okay? But now suppose that I take the number of buckets to be a bit smaller, say n to the 0.1. Okay? Now n over b is n to the 0.9. So if I have n to the 0.9 items in each bucket, then if I split that bucket into b buckets, then I have n over 0.8 items there. And now, sort of inside a bucket, I'm going to patch and then look up a level when I reach the end of a little bucket, go up 1 level, and then, okay, is that vaguely? So, okay. Yeah?
Rasmus, is my understanding correct that really what's going on is that you write n out in digits such that your string length is whatever depth you want, L, and then when you go from I to I plus 1, you are just, whichever digits are changing, you just update those digits, and each level is equal to whatever the sort of location of that digit is. That's how large the update is.
If your alphabet has B symbols, then yes. Okay, but I don't know. For me, that's not easier. But I guess from the isolating vertex, yeah, I understand. Yeah, but that's right. Yeah.
For example, if your depth was log, then this is just writing out in binary and whichever bits are changing.
Exactly. My depth was log. It's writing out in binary, but I need a smaller depth, so I need to split it into a few more things and just split it into 2. Okay. So what is the number of levels that we'll use? Well, we need this gamma to the L to be small, and we need n to the 1 over L to be subpolynomial. We can do both by just taking L to be, for example, square root log n. Okay? Then here I get n to the 1 plus 1 over square root log n. And up here I get gamma, which is some subpolynomial factor that's quite small, to the square root log n. ish, that kind of thing. Okay, I think in practice, or not in practice, but in the proof, we need like slightly fewer levels. Okay. So I want to say one more thing about this, and then I should also remember to click through the open problems. So we have not really talked about the running time. Okay, this, what I showed you, actually kind of works if you're just trying to count the number of changes that you're making. But there's something that goes wrong in terms of the running time. There is, remember, so okay, let's talk through what goes wrong, right? So I made this graph which has both maximum degree, let's not talk exactly about how you get this, but I made a graph with maximum degree delta and average degree, say delta over 2, okay? And I had n vertices. This is coming from contracting, okay? So from the forest contraction. So this delta, the average degree, if I started off in an original graph with m vertices and m edges, so like now I'm actually not making the mistake of saying things wrong, I'm just saying it was roughly a constant degree graph. Okay? Then I did some kind of size contraction by this very large factor k on the number of vertices to get the thing that I now want a spanner of with still m edges. Okay? So the spanner is being applied to this thing, okay? Which now this was the n of the spanner, okay? So the average degree is m divided by m over k, so it's k. So the average degree of this graph is precisely the size reduction factor of the overall algorithm. That's like reducing the size by something every time. This is the one number that's big. Of all of my subpolynomial factors, one of them I cannot power arbitrarily without getting large numbers, and it's this one. So this one is dangerous. Okay, it comes like sort of when you're thinking about this, you're just kind of like you're sloppily saying like, oh, this is just all small. Who cares? You know, you can have a drink while you're doing it, and then you look and you say, shit, I'm powering delta. Okay, that's not okay. Then you kind of now you get scared. Your arms, the hairs rise, and you think, okay, we cannot power delta. So where are we powering delta here? Can somebody suggest what might be happening?
Sorry, are you referring like when you split the vertices, you have to deal with all the named incident pages, and you have to, even if they are not updating, you have to deal with them?
Exactly. That was actually perfect. So when we split a vertex, how many paths are going through it? It has to be like at least, so the vertex now has like constant degree, okay? But it used to have degree delta. There still has to be roughly delta paths, or roughly k, the size reductant factor paths, floating around. So every vertex has at least delta paths going through it. Okay? And now when I do the patching, okay, then initially in the graph, I have, say, roughly delta paths going through a vertex. Then I patch. Then I might get delta squared. Then I patch. Then I might get delta cubed, and so on. And I cannot power this thing arbitrarily. Okay? So I have to not do that. Okay, now things get sneaky, and I guess we're out of time, so I won't be able to say this very carefully. But maybe somebody in the audience can tell me why, if I take a dense expander and I subsample the edges, so now like suppose that my graph, it's not exactly true, but we can get there with expander decomposition. So suppose that my graph with these delta n vertices is actually an expander, right? Which I'll get via expander decomposition. Now if I sample it down to roughly n edges, okay, so it has this many edges, I sample it down to roughly n, then I haven't increased the path length very much. Why? It's still an expander, and expanders have a path length on the order of expansion, 1 over expansion. So if it had like polylog expansion to start, it still has path lengths only grown by factor polylog. Okay. But now, when I build my embedding paths, which I'm going to do using one of Thatcher-Pohl's algorithms, okay, if I use an edge in the spanner, then I'll have like a uniform bound on its congestion. Okay, so just like I'm embedding into the edges that I kept, embedding into the edges that I kept, with an upper bound on the number of paths that I send through these edges. Okay, so it's easy for me to use Thatcher-Pohl's algorithm to upper bound the number of paths that go through edges. Okay, we could do the calculation, but we're out of time. It's not easy for me to upper bound the number of vertices that go through stuff, especially not when I start to like combine the different spanners. So now what's left is we're going to do a magic trick to get the bound on the number of paths going through a vertex from the bound on the number of paths going through edges. Okay? And it's basically cheating. The idea is that it's actually in this graph that I need to bound the number of paths going through a vertex. Okay? But it's in this graph that I'm doing like the edge bounding. Okay? But the way that I'm picking edges to put into J prime is uniformly at random. Like my sampling in the expander is uniformly at random. So then I can look over here at the expected number of paths, and then I can say it concentrates. Okay? So I get to kind of magically back out and say, well, here was an algorithm that did something kind of stupid in terms of bounding number of edge counts. But because the way it picked edges was uniformly at random, sort of back in some other graph, things average out. And this way, I end up not arbitrarily powering this, but only growing it by the expected amount, which turns out to be okay, with like some kind of high probability statement. Okay? So this way we end up by sort of inspecting what's going on inside our sparsification procedure to get like a patch that we can apply more deeply than you otherwise would. And that's pretty sneaky. So we powered delta, we got scared, then we just looked a bit harder at the algorithm, and it turns out it's already okay because of some sampling thing that's going on inside it. All right, questions about the spanner? Yeah?
So since your depth is not 2 but larger, I mean, is this a martingale or something that you need to analyze as you go down further in that?
No, we can get a high probability statement for a single patch that's strong enough. So you can think about it as like there's an expectation. If you go away from the expectation by polylog factors, then you power those polylog factors to the depth. That's still fine. But good question, yeah. Okay, so let me advertise also, sorry, before these are expert questions, but for the rest of you, you know, there's also a problem set that isn't the interior point method, but that's asking you to think through some of the expander stuff, okay? And I think this will make like at least all the basics a bit more accessible. Sorry, yeah, separate.
So here I'm confused with the type of argument. You're saying that I did some random sampling and I
Yeah.
got E prime. But now you're looking at E prime and you're saying something good has happened.
Yeah.
won't go back and say that, oh, look, even if I didn't sample, some good things are happening in the original.
Yeah.
Is that the template? But randomness does not work like this. I mean, you cannot first.
Yeah, randomness does not work like this. That's a reasonable question. So the trick is that there's a uniform upper bound on how much edge congestion we need to make on edges that we plug in here. So I can look at that uniform upper bound and then say whether like the sum of edge congestions for a vertex up in the original graph with respect to the uniform upper bound is concentrating or not. And then this thing, the algorithm that actually constructs congestions, it's not going to assign precisely those edge congestions. It's going to be a bit less. But the uniform upper bound I can know in advance. And so I can avoid this circularity that otherwise was present. Yeah.
Sorry, can I just add, like, is this the only place that requires randomness in algorithm?
In the spanner?
In
In everything.
In everything, yeah.
In everything. So actually, this part requires randomness. It can be de-randomized using the kinds of techniques that Thatcherpool hinted at a bit, and so did Deb Malaya, about like expanders, and people know how to de-randomize things with expanders. There's another random step that we didn't have time to really talk about, which is much more unusual and requires a very different kind of de-randomization. So the hard part to de-randomize, we do have a paper under submission that does it, so let's get the reviewers to say it's okay, but like in principle we now can do it. The hard part to de-randomize is that the way we pick the forest components is random. And that statement when we said that like the low stretch tree has constant probability of getting a good tree cycle, okay, this is a very difficult piece of randomness. Yeah. Okay, so let's have some open problems. Right, so the obvious one is make this m to the 1 plus little o1 into m polylog. And I wrote simple and practical. I think it's worth like just stepping back for a second and remembering that unfortunately none of the algorithms that we're talking about in this whole week work, right? Like I'm putting it a little bit bluntly here, but like roughly speaking, we're not doing very practical things, right? But I think that a lot of these things, once we get them right, they might look very different. It might not be that we can always use like a big expander hammer, a big batching hammer, but with the right arguments, there could be a real practical m polylog m algorithm. And it's worth sort of keeping in mind that I think we're doing this partly just to see what the asymptotics should be, but we're not necessarily looking at the tools that'll give us the right algorithms, right? That might be quite different in the end. So actually, I care a lot more about the simple and practical part than the m polylog m part. But I think that simple, like m polylog m is a really good way to move towards that, right? It's a good sort of intermediate step. Part of this is this m polylog m expander routing. That was how we got our edge embeddings. Thatcherpool talked about this. So some other kind of, can we improve k commodity flow using these techniques? I don't know how to do it. But Jan will tell us that there at least are non-trivial things about k commodity flow that you can do, which is a pretty weird thing because there shouldn't be in sparse graphs, but there are in dense graphs. Also, you could ask about, say, I gave you this generic L1 IPM. Can you find other things that you can do with it? And a fairly obvious thing to think about is general graph matching, except that this has an exponentially large linear program. So that gets messy, okay? But these could be some good things to figure out. I wrote in the abstract, sorry, let's go for lunch, but that I would just mention follow-up work. So there's a few things. Of course, people are like appealing to the statement, but more kind of directly building on the techniques. There's not so much yet. That's why I'm here trying to teach you all how to do stuff with these, right? But Brand, Liu, and Sidford have a very nice mPower 1.5 plus a little one-time incremental exact threshold min-cost flow. Means, for example, that you can build a graph and detect the first time it stops being a DAG, okay? And this is really by just adding edges into the IPM, okay? But they need the data structure to work against an adaptive adversary that costs them that mPower, like square root m factor. And we can also do it deterministically now. That's under submission, lots of people involved. And maybe there are other incremental, decremental things that you can do too. This we're still trying to figure out. All right, so thank you everyone for listening.
How much interior point methods were crucial for this? It seems like this work you just got rid of most of it. You got a much weaker interior point in terms of model integrations. And is it right that then everything else is just solving the update problem?
So the question was like, how much is this really about interior point methods? And I think it's correct to say that like the interior point methods are relatively easy. Like there's a homework assignment and you can just do it. Like once you have the idea, you can just do it. But what is true is that like the interior point methods are really doing some very heavy lifting for us. They're turning this directed problem into an almost an undirected problem, and then allowing us to use like all the incredible machinery that has been built for dealing with undirected graphs, like low stretch trees, expander decomposition. This really only works well in undirected graphs. So it's doing very heavy lifting, and it's doing something super weird, right? Because we're doing these like this undirectification of the residual graph. And one way to think about that is that suppose you went completely the wrong way on an edge. Now it has like tiny, tiny flow, and the flow needs to get big. But you can only double it. You can never just make it big. So you're going to have to double it many times. And that should cost you at least a factor log m. And then kind of the magic of interior point methods is that it doesn't cost you more than a factor log m, these mistakes that you get from using an undirected graph. And that is like a very deep thing that we definitely do not know how to do without. And it would be super nice, like, so here are some more open problems, okay? Be super nice to get a combinatorial algorithm instead, one that doesn't appeal to interior point methods, but this would have to use like directed graphs directly, I think. It would also be super nice just to get a much simpler data structure, even for bipartite matching. It's pretty weird that we solved this min-cost flow problem really as a min-cost flow problem. Like we don't know how to make it simpler at all in any restricted case. And min-cost flow is extremely general. It has a lot of restricted cases. We don't know how to make a simpler data structure for anything.
So, given that like the combinatorial part of the paper essentially deals with undirected graphs,
Yeah.
I was wondering whether an intermediate step to getting an n-polylog algorithm would be to first get 1 plus epsilon approximate n-polylog algorithm for directed graphs.
So for directed graphs, 1 plus epsilon? So I think the question is, what about getting like a low accuracy algorithm for directed graphs? Is that right? So here's a funny thing. If you have a factor 2 approximation for min-cost flow, you're done. Because if you have a factor 2 like multiplicative approximation, now you solve it, then you look at the residual network, you have only half of the objective left to find, and you repeat. And then so there's no difference between exact and constant factor solutions for the directed problems, because you can just repeat it log n times and then you're done.
Is that also true if like the approximation is on the value of the flow?
Yeah. So if at least for max flow, if the approximation is on the value of the flow, then you can iterate max flow on the residual graph and get the answer. So like any approximation to max flow solves max flow completely. Yeah.
As long as it works for directed.
As long as it works for directed graphs and is getting like an approximation, multiplicative approximation to the value of the flow, say in the max flow case. Otherwise, you need like value of the objective for min cost flow.
But that might still be a way to get to the m-cost.
That it's a very good point that we don't know how to use. Like a little, yeah, absolutely. Yeah.
So the gradients are still directed, right?
The gradients are absolutely directed. So it's not really an undirected problem. There's like a very kind of careful game that we're playing where the lengths are undirected and most of the heavy lifting goes into data structures that approximate the lengths. And then the gradients are kind of ignored by these data structures. And then at a couple of different steps, like checking the spanner cycles and this cancellation in tree cycles, these are like two magic steps where like the linearity of this gradient then says like, oh, it's fine. So there's something very subtle there that yeah, so actually I think in the paper it's called the undirected min ratio cycle problem. And I got really sad and angry with the others when we wrote that because we sat down, we were debating as it's not undirected. But it is morally undirected, yeah. Okay.
Is there any other questions? We can revert all the discussions offline.
Yeah, all right.
So that's then Rasmus again for the wonderful show.